Good afternoon, good morning, or just a good evening for those of you who are in the Far East time zone. And welcome to the edition of today of the IFFR, International Federation of Robotic Research, Robotics Colloquia. I'm Bruno Siciliano from University of Naples Federico II in Italy, and I'm a member of the IFFR board. If you attended some of the past colloquias, we really launched this new program as to make our Zoom live in the post-COVID era more interactive and more lively and more fun. We've had already a few of them, and today's we have a colloquium which is in my opinion, which spans 40 years of robotics. Why do I say that? You certainly remember that at the beginning of the 1980s, robotics was defined in our community as the intelligent connection of perception to action. And why do I say 40 years? Because as you probably notice in the iconic image of this colloquia, one of the hottest research themes, which is very much the frontier of nowadays robotics, is human-robot collaboration. So we are very lucky this afternoon to have one of the world experts on perceiving, acting, and collaborating, and she is Danica Kragic. Let me introduce her formally. Danica, she is the director of the Center for Autonomous Systems and professor of robotics in the School of Computer Science and Communication at KTH, the Royal Institute of Technology in Stockholm, Sweden. She's also a member of the Technical Activities Board of IFFR. She's received many awards, many recognitions, funded research, including, if I remember well, a starting grant and an advanced grant from ERC, from the European Research Council. Those are the most prestigious grants that you can get in Europe. And she's been very active in our community, and she has received, as I said, many recognitions. To make the discussion more lively and as interactive as possible, we have invited 7 discussants, 7 panelists to join us this afternoon. So they will ask questions, maybe during or at the end of Danica's presentation, and I will introduce them strictly in alphabetical order. We have Veronica Arriola Rios. She is an associate professor in the Department of Mathematics at Universidad Nacional Autónoma de México in Mexico City, Mexico. Then we have Jeanette Bogg. She is director of the Interactive Perception and Robot Learning Lab and an assistant professor for robotics at Stanford University in the US. Then we have Yok Riol Choi. He is director of Robotics Innovatory and professor of robotics at School of Mechanical Engineering of Sung Kyung Kwan University in Korea. And is also a member of IFFR Technical Activities Board. Then we have Catherine Kuchenbecker. She is Director of Haptic Intelligence Department at Max Planck Institute for Intelligent Systems in Stuttgart, Germany, and a member of the Technical Activities Board of IFFR as well. Then we have Cordelia Schmidt. She is Research Director and Head of the Thought Project team at the IRIA Rhône-Alpes in France, and as well a member of the IFFR Technical Activities Board. Then we have Mario Selvaggio, who is a postdoc in my lab at Prisma Lab, Department of Electrical Engineering Information Technology at University of Naples Federico II, here in Napoli, in Italy, where I am. And last but not least, we have Jean Shao. She is the head at interim of robotics engineering and professor of robotics in electrical and computer engineering at Worcester Polytechnic Institute in the US. And like the previous colleagues, she's also a member of IFFR Technical Activities Board. So I introduced and I made the scene ready. And so the Zoom floor is yours, Danica. We look forward to your presentation, please.
Thank you so much, Bruno, and thank you, the whole IFFR board, for inviting me and giving me this opportunity. And I'm extremely thankful also to the first row panel that will help me to make this a much better presentation by also having valuable discussion about both ongoing research and also open problems in the area, which, as Bruno said, has been around for 40 years, although I would say a little bit more, and I'm going to address this a little bit in my presentation. So how far we have come.
Danny,
yeah.
Danny, forgive me if I interrupt you already. I forgot one thing. For all the attendees to the IFFR Colloquium, you can ask questions to the speaker, and the best way is to post them on the Slido platform. So I will regularly check the Slido platform. You see it in the chat from our producer. So please be kind as to pose questions during the talk, and I'll convey your questions to Danny. Sorry for interrupting you.
No, it's perfectly fine, because this is, it seems that my internet connection is a little bit unstable. Let's hope that that doesn't continue. Anyway, as you said, it's perfectly fine to interrupt me during the presentation and start a discussion on any of the slides I basically go to. So my work has been inspired by human ability to act and interact in the environment. I haven't been doing this for 40 years, just for 20, but for 2 decades, I think I have realized how advanced our ability to manipulate and interact with all types of objects and tools that we have in our houses, at our work is. And for us humans, it seems that there is almost no needed mental effort to do many of these. Now, we use our hands, fingers, we use arms in collaboration, dual arm manipulation. We use the upper body, the full body, and also when we do that, when we interact individually with objects, or when we collaborate with other people and do something in collaboration. Now that collaboration might be passive, so we just basically move things around, pick and place them somewhere, or it might be very active in terms of that forces, energies, and so on are exchanged between our body, object, and so on. In order to be able to do all of this, we also rely on pretty advanced sensory feedback, visual, tactile, proprioceptive. But none of that would actually be enough if we also don't rely on lots of experience. So how we used to do things, how we train to do them, and also lots of emotional attachment is being put in the way how we exert forces, torques, and so on, where we interact with various types of things. So what I think is very inspiring is that if we take any of these images on my slide here, we still don't have a good way of solving either the perceptual problems, the control problems, the planning problems. So I think that images like this can serve as inspiration for very many different communities, not only robotics, for quite some time ahead. Now, when it comes to interaction tasks, I would say that the majority of human manipulation tasks are contact rich. So we get into contact with things, we lose contact, we actually use contact to exert compliant motion and so on. And what is important when it comes to contact-free or contact-rich manipulations is that in the first case, we potentially do not have any exchange or forces of energy, while in the second case we do. When it comes to contact-free manipulation, we can probably do very, well, it's not maybe simple, but let's say pretty direct kinematic planning, while contact-rich tasks do require dynamics to be taken appropriately into account. And when it comes to the methodologies that we use and of course develop for addressing these, they don't come only from the robotics community, but they also come from control communities, signal processing communities, community machine learning, computer vision, and so on. The things that I will focus a little bit more on today is on why this is relevant for feedback control and how data-driven methodologies that have been, I would say, very much employed during the past decade, also in the robotics community, are potentially useful to solve some of the difficult problems, of which examples I have shown on the previous slide. Now, what I think is important to bear in mind when we talk about dynamics and context-rich tasks, we need to rely on real-time multimodal perception. So vision will not be enough. We need to use things such as tactile feedback, force feedback, and so on. And we also need to have appropriate control strategies that can adapt to potentially changing conditions. Now, what are the changing conditions? Those can be complex physical properties of the objects that are not completely known beforehand. It might be the change in state of the object. So if you apply a certain action such as chopping, there will be definitely a change, irreversible change in object state and so on. And all of these needs to be appropriately represented and taken into account. Now, if I would like to somehow put 20 years on a single slide, I use this parallel to Formula One driving. So this is from Monza. So I started with visual and tactile servoing, moving to real-time tracking, grasping, caging, mobile manipulation, and so on. I'm not going to go through all the details. And I think that what characterizes my research is that I'm basically doing the laps. So I'm driving around in this, I'm driving around like a Formula One driver, not without the team, of course, and maybe not, I'm not maybe the fastest driver. But what I think is important is that we have lots of problems that have been identified quite a while ago, and that still are considered as open problems in robotics. Now, why do we need to revisit these problems? Why do we need to understand how the work that has been done before has tried to solve them? Is because I think that there is lots of relevant work that has been done on analytic modeling and control, for example, and of course perception. But what is interesting is that the new machine learning methodologies also offer us lots of tools that can address some of the challenges that we meet when addressing problems in these different areas. And what is kind of like putting the energy into this driving where the fueling is that when I started as a PhD student with visual tactile servoing and so on, I of course started with rigid objects. But now we see that the move is very much to soft and deformable objects. Now the problems may be the same. We still need to track them. We still need to use full body mobile manipulation to plan effectively the actions on those objects. We need to also have a better understanding how humans perform these tasks. Most of these tasks will not be able, or we will not be able to execute them with a single robot arm. We will need two. And of course, as I said, context-rich manipulation, especially when it comes to soft and deformable object, is definitely something we will need to continue to address. Now, just to give a couple of examples, why do I show videos here? So this is one of the examples, I think, of the first Amazon picking challenge. Everything that we do, of course, we want to have a nice underlying theory with all the proofs that we need for our controllers. We want to have perceptual algorithms that generalize and so on. But they also need to be effective. We need to be able to effectively execute tasks. Robots need to do this as fast as possible. They need to be able to adapt to changing environment. And also, if there are errors, they need to be able to replan their actions when errors are detected, so to resolve them. The techniques that we use, of course, then rely on the integration of the strategies or of the problems or the approaches I have presented on the previous slide. Also, some of the tasks that we would like robots to, let me just stop this one and start with this one, might be, let me see if this plays, might be too difficult to model analytically. So in order to understand how to throw a ball on a object here, it happens to be a Pokemon, it's a couple of years old work, we need to really understand very well the hand-eye coordination, the dynamics of throwing and so on. And having an analytic model for that may just not be feasible to design. So machine learning strategies and ways of representational learning can be very effective when there is a high complexity in tasks we want to address. Now, I have been speaking a little bit about multimodality, and I want to visualize it with one more example. Now, when it comes to robotics community and applications of robotics technologies for the future, and there is a lot of promise, I would say, in human-robot collaboration. Now, partially for the purpose of robots learning from humans, or robots even teaching humans how to do things, doing things also together, leaving humans to do those things that humans are good in, and then supporting, as a third hand, human activity in natural environments. Now, in this particular case, observing a human baking is not all that easy. We don't still have good models of representing the state of something such as dove that really changes a lot. And even relying on vision-based methods for hand tracking in cases where the hands are covered with flour or covered by this let's say, very deformable object is still very difficult to achieve. Now, except just observing visually and passively helping, the robot wants to also engage in the interaction with the human. So having a dialogue, explaining what the human is doing, what kind of help it needs, it's something that would be needed in a scenario like this. Now, there are other types of collaborative tasks that are maybe more of, if I can say like that, kinematic nature. So humans getting help from robots in carrying things around. So in order for this to be done efficiently, the robot needs to understand something about the human body. It needs to understand the movement of the human. It needs to be able also to understand its own body. So whether a certain activity brings the arms close to singularity, and address that in a proper way without scaring the human by having kind of like jerky motions and things like that. So I don't believe that it's not easy to solve these tasks only by relying on a single sensory stream. And I think that most of these tasks are extremely difficult to solve without also using conversation or dialogue. The robot, especially when it comes to untrained user, will need to explain to the human what it is about to do, why it moves in a certain way, and somehow signal its planned behavior so that the human doesn't get scared, or that the human itself or himself generates some form of a jerky motion that again can result in a rather strange behavior from the robot part.
Oh, hello, Daniel.
Yeah.
I'd just like to know, hi. I'd just like to know a little bit detail about this interaction. It's very interesting. So how does the robot know what the person will need, what ingredients? So what kind of gesture or signal the person gives the robot? It's not too obvious.
Yeah, do you mean in the second example with the human-robot co-manipulation?
I'm actually talking about this baking example. It looks very interesting.
Right. So this was just more as a from the purpose of motivating the problem. So what we are looking into are just a rather simple dialogue-based interaction, where the human has a set of, let's say, predefined. It follows a recipe. So they have a task from a recipe, and the human basically starts with a set of activities or actions related to the ingredients that stands in the recipe. And then it asks, for example, okay, now I need sugar, now I need, and so on. And then the robot can use that information to identify the right ingredient and give it to the human. Now, this is very, I would say, just a motivating example, because the issues that we have here from the technical side is, how does robot understand how to actually shake the box with sugar and shake the box with cocoa in order to provide the right amount of the ingredient to the dove. I think that, you know, we thought, okay, it should have a small spoon and it should take things out and then it should measure, but it's too difficult. So I think that, you know, just the issue of shaking and making the right, the relation between how much of the powder is coming out and the shaking, I think it's an interesting dynamic problem in itself.
Very interesting manipulation, actually. Yeah.
Yeah. So thank you for thank you. Now, there are a couple of other things that I find interesting. Of course, you know, I would say that the whole grasping area has been a little bit not negatively perceived, but grasping has potentially been considered as a resolved problem. I don't think that that's actually the case, because when we interact with the environment, we don't just grasp things, but we actually plan how to grasp them. And that plan is very much dependent on the way of what the robot is supposed to do with the object. So here I'm just demonstrating, you know, this is like 10 years old video or something like that. We address the problem of pre-manipulation. How would the robot first plan how to reorient the object so to be able to grasp something from the surface that is very flat. So I think that this type of planning is something that humans do almost without a mental effort, but we still don't have, I would say, good credible strategies for all types of objects, for all types of tasks where robots can engage in that pre-manipulation in an effective way. And then finally, also looking into more human-robot collaboration part, and it's direct physical interaction where we looked very much into co-adaptation. So this was a result of one of the EU projects we were engaged in. So it looked into how much time one would need for the robot and the human to entrain themselves. So the task here is to move the ball, to have it at the end of the movement, at the middle of the board. So the idea is that the robot and the human collaborate in order to achieve that task. They know what the task, what the goal is, but now they need to basically adapt the velocity and the movement so to achieve that. And I think that that's also kind of like an interesting example, which we have very many of, different types, where it's not only the human that acts as a master and defines what is to be done, but the robot needs to collaboratively also provide its own, based on its own capability, it needs to commit to achieve a certain type of a task. Now, I want to say a few words on hardware, because I think that in most of these videos, you have seen, well, not all of the platforms, but many of the platforms that, or generations of platforms that I have gone through. And I have always tried to engage or use dual ARM platforms, because I think that that offers us a more ability to address a large variety of tasks, and also platforms that are mobile. And Bruno has mentioned, yeah.
Now, before you go on hardware, I just collected one question from Slido that you might find appropriate to answer now. Daniel Burszka is asking about when you say data-driven perception, do you mean to use this only in the mapping and the labeling of the scene, or also as an error correction in the control loop or manipulator? So is there any error metric in the machine learning techniques that you are using for data-driven perception?
I will come to that when I give examples of chopping and hacking or cutting tasks, because I think that this is exactly what, thank you, Darius, long time not seeing, I miss you. It's an excellent question, I think. I think that we need to, and this is the whole idea of this interactive perception, we need to have a better understanding of what varies while a robot is executing a certain task. And I think it has to do with interpretability, something that computer vision and machine learning communities are addressing very much today. I have a couple of slides on that at the end. But it is definitely something that we need. We need to understand what we can measure and then what is relevant for the task. So I'm going to talk a little bit also about latent models and how that can also be used to kind of like make a more effective representation for the perception. But I wanted to say something about the hardware, because I do like to do things on real robots, but you know, after 20 years, it is a little bit frustrating that you know, we need to buy a new robot platform maybe every 5 years or so on. And in despite, I would say, the developments that we have seen on the side of the mobility and drones, there is very little that we can buy when it comes to the off-the-shelf hardware regarding the hands. Now I have this fantastic work from Biki's group. They did a century of robotic hands in the annual reviews of control. Only the table is actually open source, but if you want to read the whole article, I think it's very interesting. So they provide a table of all the hands that have been reported in the literature since 1912. So it's, again, a century of, okay, maybe the first hands were not really robotic hands, these were prosthetic hands, but still, people have been building, designing hands for a really, really long time. I mean, this list is longer than any list that we would be able to produce of robot arms, for example. So I'm just a little bit frustrated that we don't actually have better hands, hands that are equipped with sensors, actuated, under-actuated, covered with sensing. Doesn't really matter, but I think that this is one of the big problems in the area of robotics, having also the appropriate, let's say, hardware that is reliable, robust, and so on. So I would say that the serious attempts of building hands have been going on for actually 60 years. Somewhere in the 60s of last century, people have started to build the hands. And the table continues, as you can understand, to 2020s. So I think it's an amazing set of works that has been summarized here. Now, why am I mentioning this? 60 years. Is it a long time? I don't know. So I'll try to make a joke and maybe nobody will laugh. But 60 years of Formula One. Okay, 1960s, last century. So this is an example of how it looked for a driver to go to a pit stop. You see there are a couple gentlemen around, one of them doing some really heavy work there in the background, exchanging the wheel and so on. And yeah, it does take some time. The guy has also the time to get some coffee and so on. And then look at us how it looks nowadays. The car gets in and the car gets out and the job is done, right? So I feel that this is a little bit what happened to robotics, you know. We deal with good old problems. There is a little bit more people involved. Things happen a little bit faster. But not much has changed. I'm not going to comment on the gender issue in this particular area here, but I think that it just shows that there are problems that in the beginning of the, well, in the beginnings of robotics or even now, I think that we are underestimating both the effort that needs to be made, and also how that effort should be made in a more collective, in a more collaborative manner when it comes to researchers. Now, why is that? So I've been using this video, and I'm going to continue to do this for hopefully next 10 years too. I'm not saying that, you know, I would like to have a robot that does this. Dishwashing, we have dishwashers, although my husband says that this is a task he cannot do. But anyway, I think it's a fantastic example of where grasping, interaction, dual arm manipulation comes into play. So the human here uses hands as a tool. It manipulates another tool, this sponge, right? It is, he is able to adapt the forces and the torques to the friction conditions that also change, right? If we have oil on porcelain or on metal or on plastic. And of course, you know, I talked a little bit about this emotional aspect in interaction tasks. If you have something that is pretty expensive in your hand, like a very expensive porcelain bowl, you will probably not put it in the dishwasher. You will wash it by hand, and you will do it very carefully. So this, or if you have a dangerous object in your hand and so on. So all this knowledge here is something that is somehow trained or innate to humans. Well, not maybe innate, but is definitely trained. That is still very difficult for robots to do, especially when it comes to, again, interaction in different media, which also most of the robots won't be able to do in water, oil, and so on. Now, what can we do when it comes to in-hand manipulation? Yeah, there have been examples of actually moving, reorienting objects, and also work that can adapt to both changing properties of the object and external forces, doing regating, squeezing harder, addressing the issue of, as I said, regating or regrasping. I think that all of that is interesting, but as most of you know, especially those working on grasping, this requires quite some time to set up the system, to get the necessary, in this case, tactile feedback to understand how much force I can actually exert on this object until it breaks. And where just exerting more force is not enough, but that actually I need to grasp it in a different way in order not to lose the object from the hand. Or if the external forces or the weight is too high, I would also need a second arm or a second hand to act as a support. And all of those interesting problems, I think we still need to find a good way of how to solve and generalize over different platforms and over different types of objects. Now, that's why I think that all of the problems that you know, we see maybe as grasping, caging, in-hand manipulation, and so on, they need to be put into context of an integrated system. So we need to understand how to actually pre-grasp something in order to be able to maximize, let's say, the way of re-grasping or gating the object once the external forces start to act on that. And once it has been grasped, also have the ability to then do online control. It goes a little bit into the direction of what Darius has asked. Many of the properties of the objects will not be known maybe prior to actually do post-grasping. We will need to understand something about the friction, weight, and so on. So that needs to be estimated. That needs to be reused, let's say, in the control strategies. And if we don't have the appropriate sensing, so if our tactile sensors cannot sense shear forces, it is of course necessary to use other types of sensors, such as vision, in order to understand whether the slippage has occurred, and be able also to have systems that choose the appropriate feedback in order to, let's say, fulfill a task or just keep the object stable in the hand. And now one needs to kind of like have in mind, okay, is this realistic? Do we need that? Of course that we do, because not all of the tasks that the robot will be tasked to do, especially not in the environments we are envisioning robots to have, outdoor and so on, to pick something up and place it somewhere else. Lots of things will be about tool use. The robots will need to hold something and exert forces on other types of objects. So this is why I gave you the example of dishwashing, right? They will need to think how to actually also consider maybe the object or the tool as a part of their body, extended body, and use that to devise appropriate or choose appropriate control strategies based on the relevant perceptual input in order to be able to execute tasks. Bruno, if you want to go and jump in with a question, I'm perfectly fine to do that now.
Yes, let's have maybe a first quick round with any of the panelists. If anyone wants to, otherwise I have one which I collected from Slido. Although I don't know, it's like this question is by Anonymous. Do you use some haptic and visual feedbacks in the control loop of the robot in these experiments, or the actions performing these actions are predefined?
No. So everything is with feedback. So in this particular example here, the work that we did with Ud Billard's group, which is on in-hand adaptation, for example, this one, it used the SynTouch sensors to actually measure the forces and also the vibrations, and uses that to basically do stiffness-based control. We also use a force torque in the wrist to understand the external forces that are acting on the cup. In this particular case, fiducial marks are here, but we are actually using visual feedback to understand the pose of the object in the hand in order to be able to plan the reorientation. So in these examples, everything is based on single or multiple sensory feedback.
Danny,
Great.
can I ask a follow-up question? This is Catherine.
Yeah.
Let's go to the picture on the right here. I liked the contrast you were making between the SynTouch BioTac, these like biomimetic fingertip sensors, and the force torque sensor. I find that my students, the force torque sensor makes a lot more sense to them. They know the units and that you can draw a vector, you can really make sense of it. And the BioTac, the signals, even though you said it's not a force sensor, it's impedances through the fluid, it's these tactile sensors, it's complex. What do you have an opinion on? Do we need both of these kinds of sensors? Does it really matter if the sensors are interpretable from an engineering standpoint? Do we need the multiple modalities?
I'm kind of like of a belief that we should try everything and then have a good ways of assessing how relevant it is for various types of tasks. So I think that, you know, when it comes to slippage, for example, I think it's extremely difficult to detect slippage with solely a force torque sensor, or when you do things and you interact. For example, we have a couple of examples of actually using tools, you know, and mixing things in a bowl or something like that. Tasks like that, you know, as you know, I mean, force torque sensor might be okay, but everything that has to do with reorienting things in the hand or potentially, let's say, applying actively forces, like in this particular case, we do squeeze, we do like look into the stiffness and try to understand you know, how much, there is an upper bound of how much we want to squeeze in order not to destroy this plastic mug. But all of those things, I think, we need to have the fingertip sensing. And as you said, these sensors are extremely expensive. They're filled with fluid. They need to be recalibrated all the time. You actually need to have a syringe in your lab to actually add the fluid in them. And this is what I meant when it comes to hardware. I mean, I feel like a medical doctor when I'm fixing my robot rather than as an engineer. And then, you know, you need to build a whole framework for recalibrating this, having a set of objects of different materials in order to understand, you know, how the force that you exert actually corresponds to the measurements that you have. And until you start to do that, and still you really start to, or try to build benchmarks, you don't understand, you know, what you can actually do. Now, from the machine learning point of view, I think it would be interesting also to kind of look into disentanglement as a scientific problem. So try to understand, you know, out of all these measurements that I have, are these representative for the task? How are these representative? Can I use them as generators for the you know, control and so on? So I think we should still encourage everybody to use as many sensors as possible, but really try to choose something that the whole community can use robustly, so that we don't have all these kind of like tedious processes of calibration and so on.
Thanks.
Okay, so I'll continue, but please stop me anytime. So some of the recent stuff that we tried to do, you know, is adaptation in cutting. And I wanted to go back to a little bit what Darius has asked. And again, this is extremely difficult. It's not only that it's difficult from the purpose of, you know, model predictive control maybe doesn't work, open loop strategies don't work because, well, as you know, not all the potatoes are same, not all bananas are same, not all the squashes or whatever, zucchini are the same. It's not only that. The potato is actually not uniform in terms of stiffness or in terms of hardness along its, well, the whole body, if I can say like that. So I think that this is really, these are some of the representative tasks that are extremely difficult to do. Now, again, you see another robot that we are now using for this type of task. It's ABB Yumi. For this purpose, in order to be able to exert forces that are actually needed to cut really hard stuff, such as potatoes that also have lots of like sugar, you know, that gets the knife stop moving, or carrots. The robot couldn't actually exert the forces that we needed. So I think that this is also an interesting problem that one needs to address. Maybe the robots won't cut in the same way as humans. Maybe we need to choose various or different types of cutting strategies, so that the second hand is not just steady holding the object, but it's rolling the object while the hand is cutting. So there are so many interesting things, I think, still here to address, and that goes a little bit into the direction of what you, Catherine, have just said. It's not so much about doing the things in the same way as humans do, but trying to understand what are the plausible strategies that we can actually have on robots while cutting. So in this particular example, we actually use only force torque measurement as a feedback. And as you see, one of the hands is firmly holding, or well, the object is held firmly on the table, although there is some motion going on. And this is not modeled in any way that the object moves, but it's compensated for in the model. And in order to be able to do that, as I said, we can't use the classical model predictive control or anything like that. We do have examples that the robot learn controllers from number of examples, and that then learned models are actually deployed online. Now, one of the problems we have here, of course, when it comes to learning dynamics and learning the models that are data-driven, something like CNNs and so on, it's really to understand what is that the CNN is encoding. And that, again, goes into the direction of, I think, Catherine's question and a little bit into Darius' question. Yeah, we learn something, but we don't necessarily know what exactly. How is that related to exactly to the perception or to the measurements? And we don't understand completely to what set or how wide is the class of objects to which these controllers apply. So you can't use the same controller for cutting the potato as with zucchini, because if you have a fresh zucchini, of course, it will be very soft. So it's not only about how much force do you exert, it's also about the velocity, the type of the movement of the knife, and so on. So it does call for kind of like data-driven methodologies, but again, it's not maybe easy to understand the generalization principles.
Hi.
Let me, yeah, go ahead.
Yeah, I have a follow-up questions from Darius Buska. which is also relevant since you mentioned the dynamics of the object. Is asking about the assessment of physics of the manipulated object and also for the capabilities of the human partner. So shouldn't we focus on physics first before we work on planning? Because he says his point is most of the manipulation is based on passive sensing and just geometry. So what about, I mean, is there any way to incorporate the physics of both the object and in case of a collaborative task also of the human partner?
Yes, absolutely. I think that this is actually an extremely important problem, and it has to do with representational learning, something that I wanted really to come to a little bit later in my talk, right? So what is that we represent, and how can also, as you say, the aspect of human be used here? I assume that he means in a collaborative task, so that the human in a way helps and things like that. No, I absolutely agree. Our approach to this is try to understand. I mean, one big problem right now is that we don't have simulators that can simulate this for us. There are no simulators that can, in a credible way, simulate in a good way the physical parameters of something being cut. To do this in a temporal manner and then apply them to real strategies. So we have spent quite some time trying to understand where do problems actually come from. Do these problems come from the exerted, let's say, actions on the object? Or do these come from the, let's say, the fact that the physical parameters of these objects actually change, let's say, in a very non-linear way, so that this is not something that we can actually just with, again, the data that we have available in a credible or in a good way. I think it's there are many things here, right? So because you can always change the knife, you can have a knife that is what do you say, tinier in a way, or sharper, and so on, and all this will affect what your network in a way learns. And again, we do this online. Maybe I'm not aware of a plausible simulator, but I would really like to simulate kind of like realistic conditions of these types of objects. It's also something for our community to continue to address. In the interest of time, I think I will just jump a little bit over the aspect of complex tasks and how even simple specification can change kind of like the workflow or the system parts that we need to have. And I wanted to say a little bit about state representation learning. State representation, of course, something that we have known and dealt with in the robotics community for quite some time. And then the whole aspect of representation learning, to some extent unsupervised also representation learning that comes more from the machine learning community. And one of the trends, of course, that we are looking or seeing in the community is disentangled representations. So the representations that can, in a good way, disentangle the underlying factors of variation in order to better understand what actually matters. What should I put my controls on? What should I measure? And so on. And of course, there are different ways of how domain knowledge and various types of generic priors can help in that process. So what I'm trying to say here is that I think that in robotics community, we really need to be smart. We need to use all the knowledge that we have about the physics of the process, right? We should try to use that knowledge and in the process of let's say, modeling, and not only do things in a completely data-driven way. I don't know if this, to some extent, also addresses what Darius has asked. So it's a kind of like golden middle between building on what we know and then having the data-driven part more account for parameters that we don't know of affect the whole interaction. And
can I ask a
yes,
question?
Absolutely.
For you, how would you say where you would want to use domain knowledge and where would you want to use learning? And in particular, what kind of modalities do you feel like learning would help you most with?
So I think that, I mean, of course, when I talk about sensors, vision is a very powerful sensor that has been used extensively in robotics. But when it comes to some of these interaction tasks, of course, that we need force torque sensing, maybe to some extent also tactile sensing. It depends. Now, the space of this measurements is much more difficult to understand, right? When we try to understand what an image represents or what do I see in an image, when we talk about interpretability, is maybe easier because I know in a way what I want to represent and so on, but it's much more difficult to think of in these terms when it comes to force torque and tactile data. So I think we need to understand whether there are ways of using the models from the interpretability perspective, but on the data that is not visual. I don't know if this completely addresses
yes.
Yeah.
And maybe one more question for this cutting example, which you just showed before. Do you just measure, you learn the data representations for the sensors, for the torque sensors, or you also have a vision model, or how do you?
There is no vision here. There is no vision here. We only measure the force. And then we control basically the velocity of the robot. So this is a velocity controlled robot, so we can't control torques, for example, here, which also is an additional problem. So strictly force measurements, and then controlling the velocity.
Yeah, because if you had a vision sensor, you could probably determine also some of the properties of the objects already, right?
Precisely. The question is whether these are then, to what extent these are important for then exerting or controlling basically the velocity on the object. Of course, you can say, oh, we know what it is, we can identify it, and from that perspective, you can then choose the appropriate controller. But there is still a big problem with adaptation. Even if you know it's a banana, you don't know whether that banana is green. Well, maybe you know from vision, but the green bananas are just a little bit harder than yellow or bananas with black dots on it. And that if you use the same type of force on a soft banana, you will basically squash it rather than actually cut it. So I think that these are the things. If vision, again, could give us information about, for example, the physical properties such as softness with a high accuracy, and maybe it is possible, then I think that from that point of view, it could be used as an input directly to the controller. We haven't found yet a good way of how to actually do that, apart from just the categorical information. And that is that we do have different controllers for different categories of objects.
Adi,
and then
I'm sorry, go ahead.
When you cut the banana, but then you have some force feedback or not? Because then you can
Yes, on three of them, on all of them is force feedback. So there is a force torque sensor in the wrist of the robot, which you don't see.
That could give you additional information, for example, for the banana, if it's soft or hard, right? So basically,
and this is exactly what we are using. So this is how we learn dynamics. So
you could learn it jointly, right, from the vision and from the.
No, in this case is precisely solely based on the forces. But if we learn it jointly, maybe that would make things again easier. Absolutely.
Okay, thank you.
Yes, I also see a question from Rosena Baisi.
Oh, Regina is here. Oh, she always asks difficult questions, but yes.
this is a sort of fundamental question, and the question is like the examples you show are all task driven. So she's always worried about the youngsters, specifically the PhD students. So how would you partition the problem where you can clearly identify foundational issues in system identification, in modeling and control?
Yes, exactly. So I think that the title of these two papers, both of them are from 2020, our recent papers, somehow define also the areas and maybe answer completely the question that Regina has asked. I think that modeling and learning dynamics for, let's say, rigid to soft objects, or rigid to soft structures. I think that would be a really nice title of somebody's PhD, so that you actually vary the stiffness of something or the hardness, and then you have a control theoretic approach to it, where you, for example, address, okay, if the distribution or the softness is uniform, then this type of model predictive control can potentially be used. But if you have something that has a really hard skin, like a lemon or a banana, where that hardness actually varies, and for many of the fruits, it will be also in a non-uniform way. If you think about fruits that have, what do you call them? Well, hard parts inside. That in a way changes. So I think that one can be very much creative about what is the structure that you try to cut through, and that you look into how you can adapt in a way your controllers that you have maybe learned on a similar type of object while you're cutting. So it's not so very much about the task. We really want to understand how the physical properties of these affect the choice of the models that we are using. Yeah, hopefully it addresses. I will come a little bit more to that when I start to talk about the interpretability later on.
Okay,
now,
go ahead.
Yeah, so, and I think that this also goes a little bit into the direction of what Regina has just asked. Yes, we need to kind of like think of problems that are task relevant, but that also generalize over various types of tasks, right? Because we cannot assume that the robot will always know or have the experience of have interacted with exactly the same type of object, fruit of the same size, and so on before. We also want to do these things embodiment independent. So again, in the direction of Regina, I mean, if I learn how to use it or how to do this on a velocity-driven robot, we should be able to transfer that to a torque-controlled robot or vice versa. We should be able to also do this between Yumi, Baxter, PR2, Franca, and all other robots, right? So what I'm looking at is how we can do embodiment independent controllers that actually are able to do that. In the direction of Cordelia's question, I think it would be nice to show that a robot that has maybe, you know, force torque sensor and tactile sensors and visual sensors, it can deploy all this data, but it has such representation that it knows which measurements to use when. So it should be able to identify where it is in the process of doing something and deploying or using the right type of measurements to resolve the problem or to execute the task. And this, I think, has a little bit to do with disentanglement, but I think it needs to really, we need to really also understand the physical properties of things in order to be able to do that. Then also the adaptation, it should of course happen online. When we encounter something new, we should know it's new, and we should be able to have a model that somehow stores that data for next time. So how do we know it's novel? How do we know whether it's something that it should completely update the whole model, or is it just something that happens very seldom and things like that? And maybe what Darius says, the experience from humans can be very valuable here, because the human can say, well, this doesn't happen so often, or this is how you resolve it, and things like that. And we need to be able to actually do this for a whole variety of physical parameters. So go from something that is rigid to soft deformable and so on, and be able also to, in a good way, have a representation of this irreversible states, right? So when I chop something, it will go for something that is, let's say, one object to many objects. How is this relevant? How does this affect basically the planning and so on? And then, of course, as everybody has says, physical parameters beyond shape. And now there are many methodologies that we have employed to do this. Of course, combination of an analytic and data-driven approaches, because I don't believe in solely analytical or solely data-driven. We need to find a way of how to combine this. By the fact that we use various types of kernels, priors, regularizers, latent space representations, seam-to-real transfer, and so on. There are many methodologies today that actually can be used. So I wanted to give a little bit of insight. Bruno, I know that I need to stop. So when it comes to the properties that everybody has mentioned, these are some physical properties, of course, of the objects. Or geometrical, but there are also representations that can be topological in nature, and that these can be also very much relevant for all sorts of different tasks that we do. So grasping things or caging things, it can be about hooking things, helping humans to come out of the water. It's not really about grasping. It might be more about caging, making sure that we have the interaction or linkage between structure. So these are some of the problems that we looked into, how that can be used, again, for controlling full body motion of not really a humanoid robot, but a full body robot, but also for interactions with objects that have loops, for example. So I wanted to show a couple of examples where the geometry kind of like plays a role. So this is now 7-8-year-old work, where we try to look into this, exactly what I say, geometrical representation of grasps and shapes. Are there parametric representations that can allow us to have a space of grasps and shapes in which we can transfer stable grasps? So if I know how to grasp a book with a 3-fingered grasp, you see the normals here, you just kind of like one grasp, a stable grasp that can be applied. How can I, by having a relevant continuous representation, actually move in this representation space as the, you can see here, as the shape changes in some parametric way, and the 3 stable grasps are, well, one stable grasp with 3 fingers is remained. I think that this is very interesting. Of course, it opens for the development in very many different ways. It's not taking into account the embodiment, so whether these 3 grasps can be achieved by any of the available hands, but it could be something that we address now with more data-driven methods and try to look into, okay, how should the kinematic of my hand look like in order to be able to continuously grasp this set of shapes? Is this relevant? Do we have this type of kind of like changes in the interaction? So one of the images in the beginning was, you know, pottery. This is exactly what happens when you have a rotating table and with your hands, you're kind of like controlling the shape of something. It may be same example when you blow a balloon, feel something with air and you want to keep a stable grasp of it. So there are all sorts of kind of like tasks that can motivate the kind of like the representation. Here we did not think about those. We thought very much from the mathematical point of view. How can we use this parametrization? What is the class of objects that we can represent with the cylindrical coordinates and things like that? And then do assessment of how the friction, for example, affects the stability of grasps and so on all sorts of objects and so on. I know that I'm out of the time. I don't want to say maybe a little bit about well, revisiting task-based grasping with CNNs and Bayesian optimization. We also did that recently in order to understand how to actually use or learn task-based grasping from very few trials. And then we also look into how we can use various types of priors and regularizers to understand tasks such as pushing. So for example, in this case, again, examples with Yumi, we change the friction on which the box is pushed, and we change the friction of the box. So we basically tape various types of materials on one side, and the robot needs to adapt of how to actually push something where the friction condition changes without tipping the box. So it needs to identify that the conditions have changed and appropriately in a more reinforcement learning-like framework adapt the way it pushes in order to be able to just do the pushing again and not tipping. Let me skip that. One more way of thinking of efficient representation by using a cascaded network of encoders and decoders. So here we wanted to learn pretty dynamic tasks of throwing and some picking, grasping in very few trials. So what we did, we went from high resolution or relatively images to basically a full trajectory of robot motion. So how to throw something on a particular object in the scene. So here it's basically encoding or trying to find a representation between an input image, you see the size here, and the full motor trajectory. It's 7 joints, and that basically in 20 time frames. So you understand how many trials we would need in order to actually train this space. We did this by actually using appropriately encoder-decoder network. It's in the paper for those interested, and then did lots of open loop or blinded, in a way, movements in the simulator in order to provide, let's say, suitable movement strategies for a robot, in this case, PR2. So we can train lots of things or movements or trajectories in the simulator, and then these need to be adapted, of course, to the available visual feedback. And the things that we are doing currently, visual action planning, again, we look into folding, but folding of objects that are, I mean, maybe still simple, but it's not just a handkerchief, it's not a towel. We do look into t-shirts. So how can we, again, generate visual plans, visual action plans for a robot? Let me just go to a video. I think it will be a little bit easier from that. It's about looking into latent state representation for doing planning of actions of a robot that needs to, let's say, fold the thing. It doesn't fold it very nicely, but it can find a suitable representation of how to go to a start state to the end state by actually generating a set of trajectories of picking up a sleeve, putting it down, and so on, and analyzing or understanding which set of states are reachable, or which is the state that I can reach from the current state and which I cannot, and so on. So this is also pretty, I would say, high dimensional, because we do it for very many objects. We do it also for very many different tasks. One other example is actually stacking objects and so on. So it's again relying on variational autoencoders for the representation, generative model, and latent space representation to be able to address the high dimensional visual feedback in an appropriate manner to be able to do that. So very shortly, what's next, or what we are currently working on, what I think it's interesting. I talked a little bit about the interpretability. So I really want to understand when we deploy certain controllers and when the problems occur, why problems occur, how can we address them, can we somehow visualize, and this goes again into the direction what Cordelia has asked, how can we kind of like explain what is happening during a, let's say, force-based control task and so on, or can we also appropriately assess various types of controllers that are maybe based on more data-driven methods. So we build this kind of, or kinodynamic images that are basically encoding the positions, the forces, the controls, and then we are looking into, again, we are borrowing very much from the computer vision community, which, for example, looks into the explainability, what in the network, or what is representative of a cat or of a dog. Looking into the heat maps, really trying to understand what has caused a certain action, such as, for example, that the knife got stuck. What kind of measurement brought it to it? So can I use this as a predictor? Can I see that, for example, stacking is in a way stacking? So can I see, or in my measurements that, or can I predict that the knife will get stuck or something like that? So these are, I think, also ways for us to understand these spaces that are not completely intuitive to visual sensing, to us humans that have intuitive way of understanding vision or, well, images, but not maybe force work sensing and so on. We are also working very much on the meta learning part for the purpose of actually understanding various types of kinematic structures, in this case robots, in order to be able to actually transfer various type of learned actions from one robot to another, because they have different properties. And this is exactly what I said in the beginning. It would be interesting to do and see to what extent then, well, we can have any kinematic structure learning something from another kinematic structure and so on, and how can we do this in a data efficient manner. So we have some initial results on that. The paper is on arXiv, I think, also, that shows how we can integrate probabilistic models together with variational autoencoders, reinforcement learning, in order to be able actually to do that. I'm going to skip this. We continue to work on actions and trajectories, but just as a final thing, and maybe a note to younger researchers, because this is also something Gruzina always likes to say. So I think that robotics community has also lots of methods that can be suitable to apply in another community. So we have a recent paper together with Lydia Kavrakis group, where we actually look into problems from chemistry, and in particular molecule caging. So this is very relevant problem when it comes to drug delivery. One wants to understand whether a molecule of a certain type is caged, so whether it will, if it's of the size, so that it will be kept in by another structure, and how can this be done in a way so that it can be guaranteed. So some of the work that we have done on caging and proved that something is caged under assumption that things can be modeled as spheres and so on. We have now actually published this in one of the chemical journals, actually, and showed how the methodology can be used to actually do caging of molecules, and for what type of molecules and so on. I'll end up with this. I think that I will continue to basically drive, not alone, probably not very fast myself, but I think that it's always very important to say that you need a team. Many of the things that we do are pretty complex in nature. So if there is one advice I would give to everybody, is to try to collaborate as much as possible with people that do things that are relevant for the research that you are doing, in order to kind of like make even bigger kind of like leap and contribution to the whole community. Sorry, thank you. I'm done. At least with the presentation.
Yeah, that's very nice, Dani. And I think we still, actually, Rosina is congratulating for a wonderful and very rich presentation. I just read her message to all of us, actually. And,
she's fantastic.
And I have maybe one more, before giving the word to the panelists who haven't spoken yet, so be prepared for that. I have one more question from Slido, which is again related to control. How to interface learning, I mean, this is a big challenge, as we all know. How to interface learning with classical control methods? What if the parameters control methods use are not good representations of the task?
So this precisely. So I think that this is, of course, one big challenge for everybody. But I think that what I have learned is that you need to understand both the control community. You need to understand, in a way, what your model is encoding. And then you also need to, from another perspective, you need to understand also the properties of the sensing and the properties of the tasks, if I can say like that. So I think that if you carve out a specific problem and say, okay, this is the problem I want to solve, you will always find a control methodology that you can solve it with, okay? If you make the problem small enough in a way, or as well defined, right? I think that that's just the case. So there is no point, kind of like, if your problem is well defined, there is no variability, then do the good old control. Model it, understand the physics. If you have all the measurements, okay, maybe there will be some noise, but I think that with you know, observers and things like that, we know how to address the problem of noise. Now the question is, how general do you want to make a certain solution, or what is the set of how does the dynamics change, for example? What are the properties of the objects you want to interact with, and so on? And when that kind of like starts to grow, that I think calls for some of the data-driven methods, because you will not be able to take into account all the parameters, or you will not at least be able to tune them. So I think that this is kind of like the golden middle for me, the complexity, defining the complexity of the problem. And I think that this is still what we don't have in common, I think, in between or the communities, that we like have a good agreement on, you know, what is actually the problem that we are solving. Yes, we can set up a set of equations. We say that this is the dynamics, but then there are all sorts of different assumptions we made. Yeah. And in some cases, those assumptions are not always communicated in a good way.
Yeah, yeah, that's very much on focus. Maybe some of our panelists would like to elaborate on this concept or any other issue which was discussed by Dani. So.
Yeah. I would love to ask a question. Yeah, thank you, Dani, for the great talk. I love the Formula One metaphors you used.
Monza, yeah.
Will be in 2 Sundays from now. It will be on September 6th. So this was very, very contemporary, so to speak.
Yeah.
Yeah, I like that. Yeah, I haven't thought about this, that we can go around over and over again to solve the same problems, but maybe better, or we understood something about it. Like, do you maybe have like an example for one of the tasks where you really thought like, okay, now we have the tool to actually solve it better? Like something you visited before and now you just really made like a big leap. Like, do you have an example for this?
Yeah, I think that, you know, from the perspective of, for example, visual surveying, I think when I started, we did not have, you know, access to real-time tracking that would actually be able to track large changes in, let's say, objects. So something that you see from a meter of distance, and then you basically come very close to it. I think that we now have methodologies that, to some extent, can represent that if you have eye in hand, kind of like a setup. It's still a challenge, but I think so. When it comes to real-time tracking, I'm coming back to that a little bit. I think that you were still in the lab when we started to do this simulation-based tracking, right? So I think that that's also kind of like a very interesting aspect of providing potential future states by simulating or having a simulator that simulates all sorts of, well, states of objects, and then do better tracking by doing that. I would like to see more in caging. I think that people, and maybe we should call it something else. I think that caging people see as a very boring classical geometric problem, but I think that it has lots of potential, both in the community. I mean, I'm thinking very much, you know, what Vijay has been talking about last time. You have several drones, and you want to kind of like use drones to carry something collaboratively and things like that, but you want to ensure that the thing is really caged or something like that. So that there might be kind of like interesting, let's say, challenges for caging, which still is not very much addressed in 3D. You know, lots of work is still very much 2D. Mobile manipulation, I think that we have better ways of doing planning in high dimensional spaces. I actually do think that than we had. You know, there are like better techniques. We are better in doing sampling and things like that. But still, what is mobile manipulation really? I mean, how do you define it? How do you really generalize this to all sorts of different problems and so on? So I think that there is still something to do, I would say, in every single of these tasks. And I would really love to see more benchmarks being defined also for assessing what has been done, and how then the contributions that may become more from the machine learning area solve things in a better way.
Yeah.
Mm-hmm. As a general comment, I think benchmarking is really more needed for maybe all the robotics challenges in research. Dani, can you perhaps stop sharing so that the people can see you?
Absolutely. I wanted to ask whether I can do that.
So we have the mosaic, the typical Zoom mosaic.
Yeah.
Vero, Yoke, Mario, don't be shy.
Yeah, actually, I do have a question. Mm-hmm. So you presented the problem of robotic hands as an hardware problem. So my question goes like, I want to ask you, how do you think the mechanical design of the hand is important when you want to accomplish a task? So
I think it's extremely important. I think that, I mean, there are several challenges we have right now, right? You want to have to start with something that is lightweight. Lightweight for me would probably mean that you have something that is made of combination of materials, right? If you want to also make it cheap, maybe plastic and metal together, or whatever you want to print and things like that. But most of all, I think it should be somehow under-actuated, right? You want to have very few motors being put in the hand because there are so many things you want to pack there, right? It's sensing you want to have, and it's going to be lots of stuff. And then you also want it to be robust so that it doesn't break and things like that. So I said a little bit about these gross moduli spaces because I think that there is a way of actually assessing appropriately kinematics by defining the properties of tasks you would like to do with a certain hand, right? So I think that prosthetic community has been looking into that maybe a little bit more than we, you know, what to actuate in order to give a certain functionality to a prosthetic hand. But I think we can do better. And a couple of years back, we had this work on using GPLVM to compare the space of human grasps with 5-fingered hand designs and so on. So we showed kind of like this overlap between spaces and things like that. I think we should do more of that. We should kind of like design hands, especially now when we can also 3D print them, and think more about under actuation, and just be, as Catherine said, you don't need to do everything as humans do. You can do it differently. And then with that, it comes all the methodology that you would need in order to achieve in-hand manipulation or whatever you want to do.
Great.
Okay, thank you very much.
Veronica has a question.
Yes. Danica, thank you very much for the talk. I got really interested in a couple of problems that you mentioned. The which are like very related. One was the chopping of this vegetable that is probably soft outside and then hard inside, and then conditions.
Or vice versa, yeah.
Yeah. And then there is also the milk, which they say like you're pouring the milk and suddenly the center of mass changes. And if you keep doing it the same way, the milk goes.
Yeah.
So then you mentioned that this problem that the dynamics may be changing in time. And at the end of the talk, you gave this example with the cat and the dog and how you were trying to study all the, like the characteristics in time. So I wonder how far have you gone precisely in studying these systems where physics are changing in time?
So we, the aspect of interpretability, we got it kind of like maybe 9 months ago or something like that, to try to see whether, you know, how people or how researchers in computer vision try to understand basically the nets and what nets encode, whether we could do something similar, but for different measurement spaces. Now, of course, there is a difference there because the nature of the measurements is not completely the same. So we just started the first, what I just presented is kind of like the first study we have. So we build the images based, as I said, on the position. It's just for the cutting and for pushing. And we could show that we could, for example, predict, or we could see before it happened that the knife will be stuck, or that the object that we were pushing was not pushed, for example, with enough force, so the friction kind of like would also result in not being able to push something. So it was more about, can I use kind of like the properties of, so I train a network, right? With both positive and negative examples, and then you are trying to use that network to understand what is about to happen, so that you can appropriately counteract that with your controller. We haven't tried that with these external factors, you know, when you push on a box of milk and you hold something and so on. Maybe that's going to be the next step. I can't say. We just need to assess whether this is actually a plausible way of actually doing that, identifying what in the signal is relevant. So we only have one publication, and is I think it's on archive. So yeah.
Okay.
Yoke.
Yeah, very nice talk, Danica. Yes, it's very much intuitive and helpful for me. I would like to get some comment on the sensory feedback. I accept the vision. You didn't talk about detail on the haptics or force talk or something others. So your work is mostly depends on the force torque sensor information. I think you have used the 6-axis force torque sensor. Isn't it true? Okay. Yeah, so then I would like to ask you to what should be the improvement on this sensory hardware in the future to get some more improvement on the contact reach manipulation and situations. That is my first question. And the second one is what kind of other sensory modality to improve the interaction with the robot and then active something that is a moving human or some, getting some intentions or the more intelligent interaction with the human and robot or something others.
Mm-hmm. So I think that having a, as you say, 6D force torque sensor in the wrist is, I think, very natural and very relevant for many of the tasks we want to do, especially like if you carry something together with a human. So you basically have a grasp on something, then you don't need to do any in-hand interaction. So I think that from that perspective, if you carry a table around with a human, force torque in a wrist would be enough. Now, however, repositioning things in the hand or again, applying forces on fingers and things like that will require some feedback on the fingers. I think that, and I think that this is really important, especially if we have under-actuated hands. Okay, so I think that combination of excellent haptic feedback on the fingertips with under-actuated hands would be a key to our community. And then rethink of strategies. For example, I mean, everybody's giving this key example. You take out the keys from your pocket and then you reorient the key in your hand and things like that. I think that that's a very interesting task from the perspective of reorienting the key, but also putting it in a keyhole, because you have this kind of like energy kind of like change also between systems and so on. And from that perspective, I think that you can, during that task, exchange between the tactile sensing and the wrist sensing, right? So can we do that with under-actuated hands? To what extent and so on? So I think that from that perspective, it's still very, very interesting in having sensing on fingers. And then when it comes to the interaction, I think that Catherine should say more about that, but having basically a full body haptic kind of like feedback. I mean, that would be really nice, I think. I mean, robots that kind of like have close physical interaction with humans for lifting them from beds or giving them a bath or something like that. A force torque sensor in a wrist will not be enough, because I think that you will be able to understand much more from the interaction if you cover your full body. And I think that that's something that Catherine works on, and I think it's really an excellent challenge for the future.
I think lots of people are working on. I agree, we need better whole body tactile sensors, better finger sensors with rich contact signals.
Well, not just for contact information, but what about the proximity information? You have any experience on that?
I mean, now I forgot the name of the sensor that actually measures infrared, right, and so on. I think that it's extremely important also, but it depends, you know, again, how much can you put on a hand, and what is that hand going to mostly be used for? So I think that I would really like us to think about structures where a robot can easily attach or detach a hand. And then it has appropriate control strategies to actually act differently dependent on what kind of like the end effector it has. We are not yet there. We are far away from that. But I think that this is one of the things that it will need to kind of like push a little bit the development in robotics, partially in order to have a more kind of like robust solutions when things break. You want to kind of like exchange. But also you want to maybe have a more appropriate hand to the task that you're doing right now. And you know, this is not very strange to humans, right? We put gloves on our hands to cover them when we do certain things. We also use other tools and so on. So I think it's a natural way of thinking.
Just a very final and quick question, because we have 1 more minute left. There's a question from Slido. In terms of collaboration, how much interest is there to implement models methods from other areas, just like you applied robotics methods to molecular caging? Are you aware of any other areas, or can you foresee some?
Yeah, absolutely. I think that lots of research that has been done in Europe has been a collaboration. For example, we collaborated with neuroscientists in order to understand, for example, how people, what people look at when they grasp things, and how can that be used to potentially do hand-eye coordination, right? There has been also lots of research, again, together with neuroscientists in order to understand what is the latency between using visual and tactile information. So when do you switch between visual and tactile? And that has also inspired the development of controllers and so on. The whole HRI aspect of working with people more from the social sciences, for example. But what we are also seeing from the application point of view and large collaborative EU projects, and Bruno, you can say much more about that than I, there is more and more requirement that there are end users involved in everything that we do. Okay, so today you can't have a project finance from European Union if you don't have an end user. And end users are there to basically define and make basically the plan of how system is going to be implemented to serve their purpose. So I would say that the collaboration goes much more beyond just the scientific community, but the whole society is getting more and more integrated in the, So I was actually thinking I'm going to give plenary at IROS, I think, in a couple of months. I will use actually fashion industry as a driver for doing robotics research to give examples of what can we do there. So that's going to be one example of how we can do fashion industry more sustainable.
Yeah, I would probably wrap up with quoting our IFFR president. I mean, as long as you can describe a task with the powerful operational space approach, you know, there is no limit to, you know, to apply robotics to any kind of disparate problems. So I think we have got to the end. This has been very lively, very interactive and stimulating. I hope that we had a peak of about 110 participants.
Oh,
as
wow.
I saw the figures in Zoom at a certain point. Now we have about 70. So it's like people, I mean, someone sent farewell messages that they had to go to lecture or to other. And also Jing Xiao, he apologized in advance that she had to leave half an hour earlier because she had a meeting at the hour. So she informed us that in fact she disappeared from the mosaic window of Zoom at a certain point. So I'd like to thank once again Dani for her time and also patience. I think we can have a kind of
thank you.
Virtual.
Thank you all for giving me your 90 minutes. I mean, yeah, that I have to say.
Yeah,
time is expensive.
I think, you know, just we have to think positive, you know, just I think we are exploiting, you know, just this is the positive aspect of this community, of robotics community that, you know, which is like, I could even maybe close the session with my inspiring motto.
Okay.
As you know,
keep the gradient up. Okay, yeah, I read, yeah, keep the gradient, yeah.
Okay. Thanks a lot to everybody. And I ask Dani and the other panelists to stay in the session. So this is the formal end of the broadcast session to all attendees. We'll have a quick wrap up with our IFFR producer and also Usama. And I know Paolo Dario is also on the bench, so to speak. Thanks again. And I don't see it yet in the calendar, but I assume that every 2 weeks, every fortnight, we have an event. So I assume that in 2 weeks from now, we have the next colloquium. So stay tuned to the IFFR website because we will duly post who is our next presenter and what's the topic, the challenge topic of our next colloquium. Thanks very much again to everybody.
Thank you.